you for the introduction. I'm Atsushi Okazaki, and I will talk about paleoclimate today. And I guess most of you are not familiar with paleoclimate, so I will briefly talk about the objective and problem in paleoclimate first. And then I introduce the assimilation method used in paleoclimate. And then finally, I will introduce my research. And so scope and challenge in paleoclimate. And I will focus on last 2,000 years. So the essential question in the paleoclimate is how the climate changed. More specifically, we want to know how spatial is the current temperature rise, and how does the climate system respond to external forcings. So this figure shows the time series of northern hemisphere temperature estimated based on observation and GCM based on GCM, and the shading shows the observation-based estimates, and the lines shows the GCM-based estimates. The range of shading or the lines shows the uncertainty of them. As you can see, the uncertainty is large both in observation and GCM-based estimates. So we need a more skillful estimate. That's the reason why we want to apply data assimilation to this field. However, to apply conventional data assimilation used in weather forecasting to paleoclimate is not easy because of the difference in the observation. This slide compares the observation for present-day weather forecasting and paleoclimate. First, the density. These maps compares the observation points for present day and paleoclimate. And the numbers shows the numbers of the observation for present and paleoclimate. You can see that the amount is totally different each other. And the next, temporal resolution. We cannot get the instantaneous state, but sorry, I missed the order. The temporal resolution of the paleoclimate is lower than present-day observation. What we can get is seasonal at best. Moreover, what we can get is not instantaneous state, but averaged state. Furthermore, the observation variable, what we can get, is not direct state like temperature, precipitation, or relative humidity, but the proxy of them, like treating widths or isotope ratios in coral, ice cores, and something like that. So in summary, the difficulty is that the observations are time averaged and indirect. That's the problem. And this slide and next slide explain how to assimilate time average data. The first one is online data assimilation proposed by RIKEN and RIKEN. So let's say we have observation which represent average of this orange line period. So in the offline data assimilation, we simulate that period and then take average and then create time averaged analysis. And that increment, delta x, is simply added to the first guess. And then we simulate next time step simulation. So that's the online data assimilation. And to create analysis, we basically use ENKF. And the other method is offline data assimilation. The first few steps of the offline data assimilation is the same as online assimilation. But in the offline assimilation, the analysis is not cycled to the simulation. This is allowed because the memory of atmosphere is thought to be shorter than the temporal resolution of the observation, and the effect of the previous update is lost before the end of the simulation cycle. Well, I forgot what to say. So, so as such, we can use pre-existing simulations for the offline simulation. So its computational cost is very low, and the implementation is much easier than online assimilation. So this offline data assimilation becoming popular these days. And next, I would like to explain how to assimilate proxies or indirect state. Because observation operator for the proxies are not readily available, empirical reconstructed temperature have been assimilated. I believe we introduce what is empirical reconstruction. Let's say we have temperature and time series of temperature and proxies. And using the overlapping period, we first create the relationship between proxy and temperature. And by using this relationship, we reconstruct the past temperature. However, the fitting between proxy and temperature is not perfect. The observation noise increases. And if the fitting is not good enough, we do not use that data. So the number of observations decreases. So basically, the empirical reconstruction processes reduce information in observation. Nevertheless, the previous researches achieved a lot. The most important result is that data assimilation outperforms empirical reconstruction. Well, Stiga et al. 2014 compared data assimilation-based reconstruction and empirical reconstruction in a framework of OSSE. The figure shows the correlation with the truth. You can see that data assimilation, correlation in data assimilation is colored deeply, which means that skill in data assimilation is better than empirical reconstruction. And the other important result is that online data assimilation does not outperform online data assimilation. Please note that this is demonstrated using atmospheric model, and we do not know if it is true for ocean. So as we saw, the problems are in assimilating time average data and in assimilation of proxy. And now we know how to assimilate time average data. So remaining issue is how to assimilate proxy. As we see, the reconstruction processes waste information. So we do not want to rely on that. And we want to assimilate proxy directly. But we do not know whether this is feasible or not. So we set the objective of this study as follows. The first one is to examine the feasibility of direct proxy data assimilation. And the second is compare the skill with assimilation of reconstructed data. Well, recently, several papers about direct proxy assimilations are published, and I will talk about, today's talk is based on this paper. And in this talk, proxies are oxygen isotope ratio in treating cellulose, coral, and ice cores. Well, process-based models for these variables are available, and we do not have to rely on empirical reconstruction, and we can exploit the data by assimilation. So what we did first is to develop models for the proxies. First, I implemented stable isotopes into GCM named MyROC5, which is the IPCC class GCM. The left figure shows the skill of MyROC5 with that of the other isotope-enabled GCM in Taylor diagram. So the angle shows the correlation with observation, and the radius shows the standardized deviation, which is the ratio of standard deviation. And the closer to this point, the better model does. So the MyROC5, the skill of MyROC5 is plotted here. So it is not the best, but we can say that that is comparable with the other models. And then using the output of this model, we drove the 3 isotopic proxy models, coral, treating cellulose, and ice cores. And this figure compares the correlation for correlation between simulation and observation for isotopic proxies. If the mark is colored red, the model does better. The model is good. And you can see a lot of marks are colored red. So since we do not have the other research to compare with, we cannot say this is better or not, better or bad, but it looks okay. So using the models, we conducted data assimilation for the period of 1871 to 2007 in the framework of OSSE. We used the offline optimal interpolation for the assimilation algorithm, and assimilation cycle is 1 year. The flowchart shows the flow of data assimilation, and as I said, I did offline data assimilation. The analysis is not cycled to the simulation. And then state vector includes annual mean of temperature, precipitation, and isotope ratio in coral, treating cellulose, and ice cores. Simulated climatology is used as first guess. And the background error covariance is constructed from the long-term model simulation. And the observations are plotted here. This map includes 1,000 observation points. But as I said, I only assimilate isotopic data. The number of observations is decreased to 100 per year. And then we did 2 experiments. One is assimilating proxy directly, and I said the observation error is to 2 in signal to noise ratio. The value is based on measurement error. And the other experiment is reconstructed data assimilation, in which we assimilated 2-meter temperature. And I set signal to noise ratio of 0.5. That is based on the previous researches. So I first recheck whether the method worked well or not. The time series shows the isotope ratio of at red pointed area, and black line shows the truth, and green line in the upper panel shows the first guess. So as I said, because the first guess is climatology, it is run as a horizontal line, and the bottom panel shows the analysis. You can see that analysis closely follows the truth. So I confirmed the assimilation worked well. But it is kind of matter of fact because we assimilated isotope ratio. So what we want to know is how the result of the other variables. So this figure compares the same figure as previous one, but for 2-meter temperature. You can see that analysis still follows the truth. This is because the isotope ratio is somewhat correlated with temperature at this point. And then I compared the correlation between the truth and the analysis for every grid point for temperature and precipitation. Green dot shows the observation site, and hatched is the area where the correlation is not significant. I don't know whether you think this is good or not, but as a paleoclimatologist, I think that this is very nice. And however, the highly correlated area is very confined to the low latitude, and the other area is unanalyzed, or the correlation is very low. So, but I think that the paleoclimate data assimilation is feasible enough. And then next, I compare the proxy-DA and reconstructed-DA. These figures shows the difference of correlation, proxy-DA minus reconstructed-DA. So if the value is positive, proxy-DA do better. And if it is colored blue, the reconstructed-DA is better. And you can see that the most of the part is colored red, so which means that proxy-DA is better. And you may think that that must be rely on the SNR of reconstructed DA. So I conducted reconstructed DA with various SNR, and these plot shows that the box whisker shows the skill of reconstructed DA, median and 75 and 95 percentile, and shading shows the skill of proxy DA. So you can see that if the SNR is 1, the reconstruct DA do better for temperature. But actually, typical range of SNR is from 0.25 to 0.5, which means that basically proxy DA is always better. So that is my conclusion. Okay, I should stop here. Thank you very much.